Hello, today we will talk about finding equivalent resistance of a resistive network. This topic is divided into two lectures. This one is the first one. So we have already learned in our previous lectures how to combine resistance in series and how to combine resistance in parallel. Using these rules for combining resistances in series or in parallel, we can simplify a circuit or a network of resistance and find the equivalent resistance. In electrical circuit analysis, we often need to find the equivalent resistance of a network between two specific nodes. Now, before we proceed further, let's try to understand a little better what equivalent resistance means. Let's say we have a resistive network. This network may have many resistances and many nodes. However, we are interested in the equivalent resistance of this network between node A and node B. So what does it essentially mean? If we connect this network across a voltage source with value Vs, a certain current I will flow through the network. Now, equivalent resistance RAB is that resistance which, when replaces this resistance network, this RAB is replacing this resistive network such that the current from the voltage source I remains the same. In these two circuits, if this I and if this I for the same voltage Vs remains the same, we will call RAB equivalent resistance of this network. Okay, so we simplify the network of resistances by combining resistances in series and or parallel successively until our desired equivalent resistance is reached. Okay, let's say we want to find the equivalent resistance of this network. There are three nodes A, B, and C, and we have three resistors connected 4 ohms, 6 ohms, and 2 ohms. Now, the question that we need to answer is how are these three resistors connected to one another? Are they in series, or do we need more information to decide about the connection of the resistors? Actually, without knowing some more information, we cannot tell how these resistances are connected. So, which information is missing here? We have not specified the two nodes between which we want the equivalent resistance. So, without knowing the two nodes between which we want to find the equivalent resistance, we cannot tell how these resistances are connected. These two nodes are typically called the observation nodes. Okay, so this is the message that we cannot combine the resistors without knowing the nodes between which we want to find the equivalent resistance. So why is it so? Why we cannot say that these three resistors are in series? If we look at the circuit, that is the first impression that we get. If we look at A, only two circuit elements are connected, so they should be in series. If we look at B, these two circuit elements are connected only, they should be series. So all three should be series. That is the conclusion we reach at first glance. But the situation is a little more subtle. We look at the next slide. Say we do not know between which two nodes we want to find the resistance. That is something that should be specified. We mentioned that our observation nodes are A and B. We want our AB. Now, if we look at node A and combine 4 ohms and 6 ohms in series, the equivalent will be 10 ohms, and that 10 ohms will appear between node B and node C, and the intermediate node A will vanish. So, combining 4 ohms and 6 ohms at, in series results in vanishing of node A. If node A vanishes, how can we find RAB? We cannot. So this is a series combination that we cannot do in order to preserve node A to find RAB. Similarly, if I look at node B and decide to combine 4 ohms and 2 ohms in series, the resulting 6 ohms will appear between node A and node C, but node B will vanish. If node B vanishes, how can we find RAB? So, even though it looks like 6 ohms and 4 ohms are in series at A, 4 ohms and 2 ohms are in series at B, we cannot make any of these simplifications because we will lose one of the two observation nodes. That is not permitted. There is a third option. If we look at node C, then we see 6 ohms and 2 ohms are in series. If we combine them in series, the resultant 8 ohms will appear between node A and node B, and node C will vanish. If node C vanishes, we don't mind because to find RAB, we need node A and node B. We do not need the node C. So, in this circuit, this combination of 6 ohms and 2 ohms are permitted. However, 6 ohms and 4 ohms cannot be combined. 4 ohms and 2 ohms cannot be combined because observation nodes cannot be allowed to vanish. Okay, so how do we calculate RAB? We will look at node C. We combine these two resistors and we get 8 ohms between node A and node B. This 8 ohms. Node 4 is already there. So if we now look at this circuit, we can say that 4 ohms and 8 ohms are connected in parallel. We know how to combine two resistances in parallel. If we combine 4 ohms and 8 ohms in parallel, the equivalent resistance between A and B is 2.67 ohms. This is the RAB equivalent of this network. We can also find the equivalent resistance between other two nodes. Let us consider RAC. We want to determine the equivalent resistance between node A and node C. As before, we cannot combine 6 ohms and 4 ohms in series. That will cause vanishing of node A. And now we cannot combine 6 ohms and 2 ohms either because that will make node C disappear. So which combination is permitted? If I look at node B is not important here. If I look at node B, I can combine 4 ohms and 2 ohms. The equivalent 6 ohms will be between node A and C, and node B will vanish. We don't mind if node B vanishes. So we have this 6 ohms, and the 4 ohms and 2 ohms together gives us another 6 ohms. So we can see here that 6 ohms and 6 ohms are in parallel. Again, not all three resistances are in series. We can combine two 6 ohms in parallel and the equivalent is 3 ohms. So RAC is 3 ohms, RAB is 2.67 ohms. So the main lesson that we get from these two analyses is that we cannot do any simplification of the circuit which results in the disappearance of one or both observation nodes. Observation nodes can never be allowed to vanish. If we look at these two results, the original network is the same, but we get two different results by making two sets of observation nodes. How we look, where we look, makes the resistance different. Okay, let's look at another circuit. In this circuit, we want to find the equivalent resistance between node A and node B. Here we see the resistance units are K. K stand for kilo ohms. Okay, the first step always in finding equivalent resistance is to identify the nodes. How many nodes are there? We have the bottom node, which is B. Here we have another node, and node A is extended all the way from the 12K resistance to the junction of 4K and 18K. This whole thing is node A. So we have three nodes. This L-shaped node is already named A. The bottom node is already named B. There is no name for the third node. We have to give that a name. We call that node C. So there are node A, B, and C, three nodes. Node A shape is not very simple. It looks like an L. A simple shape of a node is when it is represented by a point as in node C or a straight line as in node B. If node shapes are complex, it is difficult to identify how the resistances are connected. So we will redraw the circuit by considering simple shapes of the node. And in the redrawing, we will connect all these four resistors with the same connection as in our original diagram. So once we do that, this is how the redrawn circuit looks like. A is shown as a straight line on the top instead of this L shape. C is shown in the middle on the left side as in this figure, and B is a straight line on the bottom. Now let's look at this 12K. The 12K in our original circuit is connected between node A and node C. So in our redrawn circuit, 12K is also connected between node A and node C. This 3K is connected between node C and node B. In our redrawn circuit also, 3K is connected between node C and node B. This horizontal 4K is connected in our original circuit between node A and node C. In the redrawn circuit, we have also connected 4K between node A and node C. Finally, this 18K resistance is between node A and node B. Here 18K is between A and B. So this is very important to ensure that when we redraw the circuit, we must not change any electrical connection of any resistance. The resistance, each resistance must be connected to the same two nodes as in the original circuit. So what's the advantage of redrawing this circuit in a simple manner? It is easy to see. Now in this redrawn circuit, we can straightforward find out that this 12K and 4K are in parallel. Both are connected between node A and C. In this circuit, it was more complicated to identify the parallel connection. So if two resistances are in parallel, we can combine them. We have learned how to combine two resistances in parallel, and the equivalent is 3K. So the two resistances can be replaced by a single 3 kilo ohms resistance between node A and C. So the circuit is simplified in this manner. Instead of four resistances, now we have three resistances. Again, if we look at this resistance, we see that this 3K and 3K are connected in series. At node C, these are the only two circuit elements. So these two are in series, and we can combine them as 6K. So between node A and node B, we have two resistances in parallel. These two in series give us 6K, and we have the original 18K. So our AB is the parallel combination of 6K and 18K. This is the result. So in this example, we have seen how we find the equivalent resistance of a resistive network by combining resistances in series and in parallel. Okay, so There are some steps we will follow in finding the equivalent resistance. I can summarize the steps in this way. First, we will identify the nodes. Then we will name any node which is unnamed in our original circuit. Then we will redraw the circuit with the nodes in simple shape if needed. If in the original circuit no node is in a complicated shape, then this step is not necessary. Then we will identify series and or parallel connections, and excuse me, we will successively combine the resistances in series and in parallel to simplify the circuit. Finally, we will have only two nodes, and the equivalent resistance between two nodes will give us our desired result. In finding the equivalent resistance, we should remember 2 points. First, we will never let any of the observation nodes vanish, and all other nodes except for the observation nodes need to vanish before we can finally determine the equivalent resistance. That's all in this part A of the lecture on finding equivalent resistance. Thank you.